This is a boxfish, and boxfish live in coral reefs, and they don't particularly look like the most streamlined, sleek animal. But it turns out, if you ever are watching either Nova or Discovery Channel or something, or snorkeling, you'll see that a boxfish is capable of staying in one place despite the fact that the current or the waves are really moving over. So it's actually got a really, really low drag coefficient. As a matter of fact, it's about near 0. So if we were to model it, we couldn't design a better design. Well, Mercedes-Benz took its engineers to the aquarium one day, and they got fascinated by watching the boxfish. So they started building clay prototypes of the boxfish, put them in wind tunnels, and have never seen such a smooth flow of wind than anything they've ever designed. So, of course, they had to design one. It's called the Bionic car. And this car, on a gasoline engine, gets 80 miles to the gallon. I don't know how much that is in liters per kilometer. But it's about triple what the standard US car is on just a gasoline engine, merely by changing the flow form. Okay? Reducing that drag. It's more convenient than sitting in a sleek shark mobile, too. That it's box car. Locusts. Millions and millions of locusts fly in swarms, right? But they don't have traffic jams, and they don't crash into each other. Right? What is their magic secret? Here we have a little critter, clearly does not have a brain as big as ours, but yet can avoid collisions, right? And the way that the locust does it is it's got some neurons that are connected to its eyes, and it's basically like a little camera. And it takes a picture, and a split second later takes another picture. And if there is a bug that was closer in the next picture than was farther away in the first picture, it takes some sort of avoidance strategy, right? It swirls out of the way. So that principle of emulate, compare, and contrast, 2 pictures taken microseconds apart, has been put into cars now. It's called the Locust Collision Avoidance System. And by merely taking a scan, split seconds apart, and comparing that scan, comparing the distance of the bumper previously and now, and then the driver gets a warning in the car. An audible warning that says something's about to happen. Change it. So Volvo actually has been putting those into their cars. Mercedes doing the Bionic car, and J.R. West is the engineering firm that built the Shinkansen. This is a close-up of a moth-eye. All right. You never know where you might find your next solution. And moths fly at night, but it's very, very important that they don't reflect the moonlight, because if they were to reflect the moonlight, then they would be gobbled up by anybody flying and seeing those little white dots flying through the sky. So their eyes are incredibly anti-reflective. And if you look at a moth-eye even closer, they've got lots of little tiny stems. This is a mimic of a close-up of a moth-eye. And it's a surface coating that they're now applying, one, to computer screens, gets rid of glare, right, because you don't have that reflection. And they're also putting it on solar panels, because there's a significant amount of loss in efficiency in a solar panel when the photons that hit the panel bounce back up. And if those photons can stay captured in the panel, then they can improve the efficiency. So by looking at moth eyes, they're improving solar panels. Naturally, these products are properly named, Moth-eye and Marag. This is a close-up of a beetle. And a beetle's foot, to be specific, and even more closer are the little hairs on the bottom of a beetle's foot, which are called seta. And geckos actually have the same hairs. That's what allows geckos to climb up walls. And even though you can have a 20, 25 centimeter long gecko, it can scale glass. And it's not using suction like a frog. It's not using little micro cracks like a fly might use with little hooks. But each one of those hairs has what's called an intramolecular attraction. They're called van der Waals forces. It's kind of like static electricity. You can get your hair to stand on end. Very, very small force of attraction, but there's so many hairs that collectively, you put them all together, it's actually pretty strong. And then as you peel up one hair at a time, as you're raising your foot, if you're a gecko, or a toe, then you can begin to navigate your way across the floor. So incredible opportunities when it comes to adhesion. It's an entirely new way to think about adhesion. We glue things together, or we permanently rivet them or ratchet them or somehow stick them together. And quite frankly, that's why most of our crap ends up in landfills, right? Because we've stuck it together and now we can't get it apart. We can't get it apart to recycle it, reuse it, repair it, or remodel it, or whatever it might be, so we have to throw it away. So if we could transform the way that even we stick things together, it would be hugely powerful. You know, this carpet is glued to this floor. If it gets a stain, the whole thing has to be scraped up after the floor, not to mention the smell that comes from the glues. So folks have actually been working in a lot of different labs trying to mimic this. These guys have come the closest. They're calling it insect tape. There's others that have called it gecko tape. And that is a mimic. So look, here's the hairs, there's the seta, and there's the mimic. All right, they've got a little bit of a spatula kind of end. And they're finding with this gecko tape, they can take a piece about the size of a euro, and they can hang 30 kilos from the ceiling. 30 kilos from the ceiling on a piece the size of a euro. You peel off the edge and you use it again. All right? Pretty amazing. Not quite commercially viable, but they're working on it. So that's insect tape. Sharks. All right? Sharks are really, really efficient swimmers. And one of the things that makes them so efficient is if you look at their scales up close, their denticles, they have grooves in them, right? We like to think that smooth is the most efficient way to go, but actually having grooves increases because it changes the laminar flow. Things flow along the grooves. And by creating structures that look like this is a mimic of the denticles on a shark up close, we can actually reduce drag. They're putting this on the bottom of boats. And it reduces the drag of the boats, and it also has a little bit of flex to it, so it pops off barnacles, which are not good for efficiency of boats moving through water. They've also put a coating like this on airplanes. Airbus did it, and had a 3% improvement in fuel efficiency merely by putting this. Unfortunately, it didn't last. So now what they're doing is they're stenciling this on when they put the paint coat on. And by stenciling that on, they can create those channels, and we'll see, hopefully, that they have that same improvement in fuel efficiency. I mean, there's 10,000 planes in the air on any given day. A 3% improvement in fuel is incredibly impressive. So different mimicking forms. So even at the very micro scale, an incredible amount of things, if not even more, can happen.